Hello, Stat 300, and this is Professor Gonzalez, and I'd like to do some homework problems from 3.1, and I'd like to put this symbol in here to show that this is from the adaptive side of ALEKS. Once again, how do you get there? You go to the menu on the left, you click on Learn, and it'll get you into that side of ALEKS. And so on 3.1, there was one homework question on 3.1, HW 3.1 on the assignment side. And then there's 10 of them on this adaptive side. So let's go ahead and take a look at some of these. By the way, on the assignment side, the HW 3.1, the one problem had to do with grouped data. So taking group data and finding the mean of group data. Should take a look at that. But let's take a look at this, and I would like to give you some notes on this. So I've got some slides here to kind of just go through some of these things. There's some notation, stuff like that. So the mean of a data set is the measure of center. If we imagine each data value to be a weight, then the mean is the point in which the data set is balanced. So if this was like a big, long balancing stick or a teeter-totter or something like that, the mean would actually be this fulcrum point that makes the left side balanced and the right side balanced. And you might say, well, look at if I add up these pieces over here, it's more than everything on the left. But really, if you remember, if you thought about a big long board that had a balancing piece, if you had some data way out here, that's gonna have data that's further from that fulcrum point is going to have more pulling down weight, right? Because it's got that mechanical distance, that leverage. And the same kind of thing happens here. So it really has to do with how far these data points are away from the mean, and that's what gives us this balancing piece to it. Remember, mean is the I guess I don't know about more accurate, but the more statistical or mathematical way of saying average. So mean and average are the same things. Let's move on. So notation of population versus sample. So recall that a population consists of the entire collection of individuals about which information is sought after, and a sample consists of the smaller group drawn from the population. So a sample or a survey from the full population, right? The sample of the survey is a smaller subgroup of that. The method for calculating the mean is the same for both samples and populations, except for the notation. So we use this notation. Now this notation is called mu, and mu is the notation that's for the mean, specifically for when we're talking about the population, and then x bar is the mean, specifically when we're talking about a sample, which is, remember, a sample is a subgroup of the population. The formula for these two end up being the same thing, right? If I was going to describe this formula, I would say the population mean, let's start with that one, mu, that is a Greek letter mu for mean. It is, now, this symbol right here is another Greek letter, capital sigma, which means summing up. So that means sum up all these pieces. So essentially, when you see sigma of x sub I, that's saying take all the x sub 1, x sub 2, x sub 3, and add them up. So that sigma just means adding up those pieces. So just as you know, a population mean, or just like finding an average, you have to sum up all the pieces and divide by how many pieces you have in the population. And the same thing happens, except the notation is different. If I want x bar, which is the mean of the sample, or the sample mean, then I have to sum up all the pieces of data from the sample and then divide by how many sample pieces I have. Okay, so they are the same formula, just different notation. Another measure of center is called the median. Now, the median of a data set. The median is another measure of center. The median is a number that splits the data set in half, so that half the data values are less than the median and half the data values are greater than the median. The procedure for computing the median differs depending on whether the number observed in the data set is even or odd. If you have an odd number of data, well then it works out nice that you have, the same amount on the left as you have on the right. So if you have an odd amount of data, you're going to have one data piece right in the middle, and that's your median. That's the middle number. Now, if you have an even number of data, the problem with that is you're going to have the same amount on the left and right, but then you're left with two values in the middle. And in that case, what you do is you just find the mean of, or let's just say the average so we don't confuse that, but in that case, you just find the average of the two middle numbers, which just basically means you add those two numbers up and divide by 2. Okay. All right. The median is considered to be resistant. So a statistic is resistant. So a statistic is a number from our sample, or anyhow, a statistic is resistant if its value is not affected much by extreme values, large or small, in the data set. Now, these extreme values tend to have names like outliers and things like that. The median is resistant, but the mean is not. And one way to kind of talk about that would be, well, with a median, if I had data values that happen to be, let's say I had a 5, whoops, I want to go back to black. So let's say we had data value 5, 6, 7, 9, whoops, that's an 8, 8, 9, let's say 10, and 1,000. So the median in this case is still going to be, okay, let's see, I have 3 data pieces on my right, and I've got 3 left rather, and I have 3 data pieces on my right. So the median in this case is 8. So irregardless if that happened to be 1,000, or what if that number was just 11, it's not going to change my median of being 8. So we consider the median to be resistant to having large or small numbers. On the other hand, the mean is not resistant. And so an example of that would be, what if we're trying to find the mean of salaries of people in a bar, I guess. I don't know. Doesn't have to be a bar. But let's say, most salaries were kind of grouped. Someone had a salary of 50,000, and then there was a 60,000. And I'll go ahead and stack them up like there's another 60,000, just to kind of make it like a, kind of showing, kind of like a histogram in some ways. And let's say, someone else had a 61,000, and there was a 70,000. There was another 70,000. And we had an 80,000. So we got all these people that are right in this, you might have someone that's 100,000. But those are all, you can do some statistical work with that in terms of, they're all kind of grouped. But what if, so we have what, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 people in the bar. And then, so if we find the mean of this, if we add up all those salaries and divide by 9, the mean is going to be a nice number that represents the center of that, it's accurate, right? So the mean is nice to use. But if you have a big outlier, the mean really, the accuracy or the usefulness of the mean really goes down a lot. So let's say Warren Buffett walks in, or let's make him Bill Gates, or wait, who's the richest now? Jeff Bezos, I think, or the Amazon guy. Anyhow, one of those three characters walks in because they're in the top 5 richest of the world. If one of those folks walks in and they say, well, you say, how much do you make a year? And they say, well, I make 500 million every year. Well, now that's not going to affect the median much because the middle person's still going to be, that's only one value, even though it's a strong value, it's only one data point. But in the mean, that is going to skew our data so far towards the right. We're going to say, oh, hey, we have 10 people in the bar and their mean salary is, I don't know what it would be, but it'd probably be in the millions. And in fact, no one has even anything close to a million, and one guy has 500 million. So the mean is really affected when you have large or small outliers in the data set. And this also kind of shows us something. Let's say there's another 70,000 person, there's a 61,000, there's another 80,000. So most of the data is kind of grouped like this. Well, what happens is when you have this big data point here, what it does when we're taking a look at these graphs is it really skews it. It can really skew it to the right and make it kind of do something like that. And so the reason why I'm kind of talking about that is because we've got these data points here, mean and median, and the shape of data. Okay, so the mean and median measure of center of a data set. They measure the center in different ways. When a data set is symmetric, the mean and median are equal. So when you have this perfect bell shape or normal distribution, it turns out that the mean and median are exactly equal. It's when you have something like the Bill Gates or the rich guy walks in the bar that'll skew the data to the right. And remember the other way I was trying to help you remember that this is skewed to the right is to think about it like your foot. There's your big toe and it goes. So that's your right foot, and then this one would be skew left. It's like your left foot, your big toe, and it goes down. But anyhow, when the graph is nice and symmetric, the data is nice and symmetric. When it's perfectly symmetric, the mean and median are the same. When it's skewed to the right, the mean is pulled to the right. And you can remember our rich guy scenario pulled the mean to the right, even though the median was a better kind of measure of that center, but the mean starts becoming skewed to the right. And also skewed to the left is when let's say we have those same people. Skew to the left would be we have the same people in here in the bar, but then someone walks in that happens to be like little kid making a lemonade stand, and the little kid making lemonade makes $200 a year. So that's going to pull, in terms of means, that's going to skew us way down to the left. That's not a very good drawing of that, but we're going to have, this thing that looks pretty normal, but then it gets skewed down the left because something is so far smaller, so much smaller. So that is going to cause the mean to go to the left and the median. So the median stays at least a little bit truer to being in the middle of that data set, but the mean starts slipping to the left. Okay, mode of data set. Another value that is sometimes classified as a measure of center is the mode. The mode, I wouldn't say though, let's see, it says the mode of a data set is the value that appears most frequently. Okay, so back here, if we're talking about looking at the data, the actual mode of this data set would be 70,000 because it appears most frequent. It's the best way is most frequently, or the most copies of that. There are 1, 2, 3, 4 people with a salary of 70,000 there. So that is the mode. If 2 or more values are tied, for the most frequent, they're all considered to be the mode, right? So if we had four 70,000s and then you had four 100,000s, then there would be a tie. There'd be two modes. And then if the values all have the same frequency, we say that the data has no mode. It's all tied, right? There isn't one mode there isn't one category that happens more frequent than anything else. Mode for qualitative data. Okay, means and medians can be computed only for quantitative, for number data. However, the mode, on the other hand, can be computed for qualitative and quantitative. So, mode is something that happens most frequently. So if you had qualitative data, like I'm looking at 100 cars and I'm categorizing them by colors, well, you might have, I don't know, like 45 white cars, and so that would be the mode, because there might be, white cars has the highest frequency. Okay. Weighted mean just simply means that, well, let me just read this and I'll give you probably a real common example. A weighted mean is a mean in which some numbers count more than other numbers. To compute a weighted mean, we assign a positive number called the weight. And the weight in this formula, the weight happens to be these little W's. And then you have to divide by all the weights put together. So a very common one would be something like this. Like, what if we were adding some number? What if we want to find the mean of these numbers? You can definitely go through and add 5 plus 5 plus 5 plus 6 plus 7 plus 8 plus 8 divided by 1, 2, 3, 4, 5, 6, 7, right? For sure, that'll make the mean. But you could also view this as a weighted mean. You could also say, well, when I look at my 5s, it has a weight of what? It has a weight of 3. So I could just say 3 times 5, which is 15, instead of adding 5 plus 5 plus 5. And then 6 has a weight of 1, which you don't really need to write that because it's multiplying by 1. And then we have 7, which has a weight of 1. And then we have 8. We have 8. Darn it. We have 8. Geez, I'm having difficulty. We have 8, which has a weight of 2. Okay, and so that, and if I really wanted to show that had a weight of 1. So then I add up all those after I weighted them, and then it said divide by the number of weights. And so the number of weights here would be 3, 4, 5, 6, 7. So it's 7, which is still the same as up here. 1, 2, 3, 4, 5, 6, 7, right? 7 data points. So that is a weighted mean. And now I'd like to do some of the problems. And we'll have weighted means and all these different things. And one of the main things I wanted with this is, really get used to the idea of a sample mean being x bar and population being mu, because that becomes important when we're trying to distinguish what we're doing in future problems. Okay, so the notation does become important. So here's the beginning of our problems. Once again, I said we're doing some problems that are in the adaptive side of ALEKS. And once again, I try to really make that clear by making this gold pie chart kind of thing, saying it's in the adaptive side. All right. And by the way, the adaptive problems that you do gives you 25% of your homework grade. And then as you knock off topics in the adaptive side by doing that homework, it automatically gives you credit in the pie chart. And that pie chart, it's called the final pie progress grade, builds up. And then I think it's December 16th at the very end of the semester, it gives you that grade. And that grade is usually higher because If you get 80% of the topics done, I'll give you 100%. So I have a little adjustment for that, okay? All right, so now, and that's in the final pie. If you take a look at the grade book, the final pie progress piece is due December 16th, I believe, and ALEKS will automatically give you credit as you're going. In fact, it already gave you some credit by the initial knowledge check, and it'll just keep on ticking off topics as you do it on the adaptive side. And once again, if you get 80, we have 100% of the topics listed, but if you get 85, I think it's 85% of the topics is what I put down, 85% of the topics done, I adjust that, ALEKS adjusts that because I put it in there to giving you 100%, which is an A+, right? Okay, the following is a list of 4 measurements. Suppose these 4 measurements are respectively labeled x sub 1, x sub 2, all the way to x sub 4. Compute the following. What we're trying to do here is we're trying to get you to this sigma notation. Remember this sigma? This symbol right here. This symbol right here is sigma. And sigma. And it just means sum or add up. So the number here is telling you the starting term they want you to add up. And they want you to add up all the way up to this number up here, which is the ending or the last term to add up. So when they say they want you to add, so in this particular problem, it wants you to add or sum up the terms starting with term number 1, which there's term number 1. And they want you to go all the way up to term number 4, right? And then this little piece in here is just telling you the operation, what it wants you to do to each one of those numbers, right? It wants you to square it. So let's go ahead and do this. This is equal to the first term. What is the first term? There it is right there. It is 13. And what does this operator say to do? It says you need to square it. So it's 13 squared. Now, because of the sigma notation, because of that symbol, we want to sum it up and then go to the next term. The next term is the second term. And what is in the second term? It is 15. And the operator says to square it. So we square it. And then sigma summation notation says go to the 1, 2, third term. And the third term is 7. You can see it right under that 3, that red 3. It is 7. And our rule inside the sigma says to square that, so we square it. And because it's a sigma, it means we add up the next one. And we know that 4 is our last term to deal with because it's right there in the ending position. So we go to the 4th term right there. The 4th term is 6. What does our rule say to do? It says to square it. So now all you have to do is square them and then sum them up. 13 squared is 169. 15 squared is 225. 7 squared is 49. 6 squared is 36. Then we must sum up all these. When we sum up all those pieces, we get 479, and that is the answer. So this is just sigma or summation notation to help us understand how to do this, because as you saw with the formula, a lot of these formulas where you're summing up things, they like to use, there it is right there, they like to use, right, sigma or summation notation. To once you see this sigma symbol, we know that we have to add up all these x sub 1, x sub 2, x sub 3, all the way till you get to this last term that we put in there. Okay, going back to our homework. Number 2, each of 7 students report the number of movies they saw in the past year. Here's what they reported. Find the mean number of movies that the students saw. If necessary, round your answer to the nearest 10th. So this is number 2. And unless they're talking about a sample or something like this, we usually just use our mu because that's the population mean. So they're asking us to find the mean. So how do you find the mean? You add up all those data points, 20 plus 9 plus 14 plus 13 plus 11 plus 4 plus 19. 1, 2, 3, 4, 5, 6, 7. 1, 2, and they said 7 students. So I feel pretty good about that. Divide by 7. And this gives us what, 80 over, no, this gives us 90. Gives us 90 over 7. And that is approximately, I'll go down here, that's approximately 12.8571. And they said to please, if necessary, round your answer to the nearest tenth. So there's my tenths place, and I take a look at the digit to the right, that's 5 or greater. So this is going to be about 12. We're going to round to the nearest tenth. That goes up to 9, 12.9, and these are movies. The next problem, below are the line plots of two data sets. Find the mean of each data set. Well, this is kind of an idea of a weighted mean, because what we can do is we can say, well, we have two values that have a value of 3, right? So we got 2 3s, plus we got 1 4, plus we got 1 5, plus we got 1 6 right here, plus we got 1 7, plus we've got 2 8s. So that would be an example of a weighted mean, right? Because you're weighting those pieces. The ones that have doubles have to have a weight of 2. And so we have to divide by how many weights we had. And of course, we had 2 there and 2 there, and add them all up. 1, 2, 3, 4, 5, 6, 7, 8. We divide by 8. And we end up getting 44 divided by 8, which gives us a mean. I'm going to write down here. Data set A has a mean equal to 44 divided by 8 actually is 5.5. And then we could do it again over here. How about a weighted mean? I've got 3, 1, 2, 3 that have a value of 3, plus I've got 1, 2 that has a value of 4, and I've got 1, 2, 3 that has a value of 5. Now, how many weights or pieces do I have? I've got 1, 2, 3, 4, 5, 6, 7, 8. So when I do the math, I get 32 divided by 8, which equals 4. So the data set B has a mean of 4. And if we, found it by weighted or non-weighted, we could have done them individually as well, and we would have got the same answer. Okay, Henry has a score of 23, 18, 26, has scored 23, 18, 26, and 27 points in his 4 basketball games so far. How many points does he need to score in the next game so that his average mean is 24 points? So this would be an algebraic would be the best probably way to do this. Things we learned in algebra. And so we want to know how many points does he need to score in his next game. So we're going to we'll do a let statement. Let's let x equal the points scored in the next game. So what we want to do is we want to find the mean of all these points scored. So we have 23 points scored, 18 points scored, 26 points scored, 27 points scored. Now the thing is, we don't know how many points he's going to score in the next game, so that's why that's the variable x. How do you find the mean of 1, 2, 3, 4, 5 data points? You got to divide by 5. And we said we want that mean to be what? How many points does he have to score in the next game so that his average or mean is 24 points? We want the mean to be 24. So now this is just an algebraic equation to solve for us. So we go ahead, we want to basically turn that into a 1. And so this is division by 5. So if we multiply by 5, the 5s will reduce down. And if I multiply the left by 5, I must also multiply the right by 5. And so now we have 23 plus 18 plus 26 plus 27 plus this x. And that all equals 24 times, there we go, 24 times 5 is going to be 120. Yeah. Okay, so now we need to add up our like terms, which would be these constants. So we had 23 plus 18 plus 26 plus 27 is 94 plus, I'll just keep on writing this as red, I guess, for now, and equals 120. Subtract 94 from both sides, and we get our final answer. I guess I got to stay consistent. Final answer is x equals, what's 120 minus 94 is 26. So we just found out, what did we find out? Henry needs to score 26 points on the next game. And that is to get his desired mean of 24 points. Okay, so then we move on to the next problem. The next problem, unfortunately, it didn't tell you what to do. So I'm going to go ahead and write in the directions. It says, find the weighted mean. I believe that's what it would say. Find the weighted mean. So once again, that weighted mean, all you have to do is say, okay, we've got a score of 90, right? And how many people have that score of 90? That's our weight. Well, there's 70. And then we've got a score of 80. How many people have that score of 80? Has a weight of 16. And then we've got 70. And how many people? Well, it's 13, so a weight of 13. Okay, all that needs to be divided by the weights, and when you add up the number of students, that ends up being 36. Come on, 36. So that's divided by 36. So when we go ahead and multiply and then sum them all up, we get 2,820 divided by 36. This will give us an approximate answer of 78 with a repeating 3. And it says on this problem, well, on these problems, it's in general, it's saying that you should round to one more decimal place of the data that you're working with. And we're working with whole numbers, so we round to the 10th. Now this is repeating 3, right? So that would be 3, 3, 3. So if we're going to round it, this answer, this mean would be 78.3, and that is now rounded. So let's put a little approximation symbol there. The following list contains the number of hours that a sample of 8 middle school students spent watching television last week. Now, if they ask us to find the mean, I would have to use X bar, because X bar is the variable that gives us the sample mean. I was all excited when I read that, and then I wasn't excited because it says we want to find the median. Dang it. Okay, I wanted to use my X bar notation. But anyhow, median is something different. To find the median, you need to order the data from smallest to largest. So we go through and we look at the smallest piece, which is 4. The next one, which is, looks like I got a 5 there and a 5 there. And then what's next? It looks like I have a 6. And moving right along, it looks like 8 is next. And then 9. And then 14 and 20. Always double check. 1, 2, 3, 4, 5, 6, 7, 8. And that was 1, 2, 3, 4, 5, 6, 7, 8. Okay, feel good. Now what I'm going to do is I need to find the physical middle number. And I think we said before, if you have an even amount or an odd amount, there's something different that happens between those two ideas. But here I've got 1, 2, 3 on the right, 1, 2, 3 on the left. So when I have 3 data points on the left, 3 data points on the right, I'm stuck still with 2 numbers in the middle. So I don't have a physical middle number. So in that case, you find the average of those 2 numbers. So you just basically take 6 plus 8 divided by 2, and so you get 7. So the median, oh, I wanted to take a note on that. Okay, the median equals 7. The note that I kind of wanted to show, and I already put it in my notes at the very beginning. Let me put a little note here. Note. So this is 1, 2, 3, 4, 5, 6, 7, 8, an even number of data. But what happens if you have an odd number of data? Actually, it's a little more obvious if you have an odd number of data. Like what if we had 1, 5, 6, 7, 8, 9, 10. Well then, when you're trying to find your median, notice we have 3 digits on the left, got 3 digits on the right, and there's physically 1 number in the middle. So that would be your median. You don't have to find the average if there's 1 physical number in the middle, but if there's 2 physical numbers in the middle, now you've got to find the average or the mean of those 2 numbers. Okay, question number 7. Here are the numbers of children in 13 elementary school classes. Find the mode of this data set. Now remember, mode is the most frequent number that shows up. So I start off by, I see a couple 20s, so I get excited. Okay, I got 1 20, I got another 20, and I've got 3 20s. So far, that's really looking good for the mode. But then I do see some other double-y things kind of happening. Like I see an 18 here, and I see another, oops, I see 3 18s. So far, I've got a tie. I've got 3 20s and 3 18s. So we've got 2 modes. So then I go on and I see some 17s, it looks like. So I've got 1, 2, 3 17s. Okay, that's another tie. So now I got 3 modes. Unless there's something that has 4 to break that tie, then I'd have 1 mode. And I can see I have some doubles here as well. I've got a 16 and a 16, but there's only 2 of those. And I also see that I have a 19 and a 19, but I only have 2 of those. So find the modes of this data set. Well, it turns out I've got 1 mode, which was the first one I found, which was 20. And then I'm putting it in order as I discovered it. And then I had another mode that was 18, right? So I have 3 20s, I have 3 18s, and I have 3 17s. So that just means that I've got 3 modes. Okay. All right, number 8. Over the past several months, customers at Stymie's department store have been asking to fill out customer satisfaction surveys. In the surveys, the customers rate the shopping experience on a scale of 1 to 100. Here are 9 recent ratings. What is the mean? Okay, now in this one, I'm going to use X bar because when you're doing a survey, that is sampling a smaller population out of the total customers. So this would be a sample mean. Now the procedure of finding the mean is the same way, but we like to use X bar for the sample. All we have to do is add up all the data points, 65 45, 66, 76, 40, 65, 33, 87, and 88. We need to divide by how many data points we had, and they said they had 19 recent surveys, so I'm going to trust that there's 19 points there. You could count it to double check it. I sum up the numerator and I get 565 divided by 9. This gives me approximately 62 point repeating 7. And so it says round your answer to 1 decimal place. So that means we're going to round it to the 100th. To the 10th. And so we look at the next decimal. It's bigger. The 5 are bigger, so we round up. This is 62.8. And 60.8 is the approximate, because we had to round it, sample mean. Next, part B, what is the median of this data set? If your answer is not an integer, round your answer to 1 decimal place. Okay, so we need to physically, on part B, we need to physically organize our data from smallest to largest. So I see 33, 40, 45, 65, another 65, 66, 76, 87, and 88. Okay, I need a little drink of water. Okay, so to find the median, you're looking for physically the middle number. So I just need to make them match up. I've got 1, 2, 3, 4. What I mean by make them match up is I got 4 on the left, so I need to have 4 data points on the right. And when I do that, 4 on the left and 4 on the right, it's leaving me with 1 number in the middle, which is called the median. Oh boy, my throat is getting really dry. Sure, it has nothing to do with our pandemic. So it says that's part B. Now part C is asking us to find if there's a mode, 1 mode, or 2 modes. And when I look through the data, I see that there are 2 65s, which means 65 is the mode. There is 1 mode. There's 1 mode, and what is that mode? It's 65. All right, moving right along here. It looks like we just have 2 more problems. And these 2 more problems are more trying to get you to understand what happens when you replace a data set. How does it affect the mean? How does it affect the median? This one's saying the numbers of trading cards owned by 8 middle school students are given below. Notice that these are already in order from least to greatest, and that's nice of them. So it says, suppose that the number 617 from the list changes to 569. Okay, what happens to the mean? Well, we just, remember how you find the mean, add them all up, divide by how many pieces you have, in this case 8. Well, you're going to add up a smaller number, so this is going to decrease the mean. It's got to decrease the mean. We just put in a smaller data point. It's going to decrease the mean. By how much, though? Oh, well, that's a harder question. But what we can do is we can see, well, we started with what number? The original number was, is it 6? Yeah, I covered it up. It's 617 was the original number, and we replaced it with a smaller number, which was 569. So we want to know, when we find that difference, yeah, it's going to decrease the mean. Now, if we find the difference, we get 48. But it didn't decrease it by 48. That's just the numerator of the problem got decreased by 48. Remember the denominator, when you're finding the mean, there are 8 data points. 48 divided by 8 is 6. It decreased it by 6. Let me use red since I was using red there. So yes, it decreased the mean by 6 points. right? Okay, what happens to the median? Well, what happens to the median is not a whole lot because these numbers are already ordered from smallest to largest. We put a number that's only just, well, whoops, reorder it. If I reorder it, that just puts this number here, and that puts 601 there. And it doesn't really matter, it doesn't change the median because the median is still going to be physically 1, 2, 3, 1, 2, 3. It's going to be between those two numbers, right? Because that's the median. So that didn't change the median at all. So the answer is, what happens to the median? Stays the same. All right, question number 10, our last question. A reporter has recorded the ratings G, PG, PG-13, or R of each movie played in a theater over the past year. Which measure gives the most common rating? Well, what of these three measurements, mean, median, or mode, measures most frequent? Well, that's going to be the mode. So the mode measures when you have copies or most frequent. She has recorded the number, this is part B, of miles. Oh, Shen, I'm sorry. Shen has this really tiny writing. Shen, maybe I just go like this then. Yeah. Shen has recorded the number of miles he has driven for each of the last 10 weeks. Which measure should be used to summarize the data? Okay, so whenever we're trying to find the center of something or trying to summarize the data by finding the center of something, mean is probably the best to use unless you have outliers. Then it's going to be median because the median is resistant to outliers. And when I look at this data, it looks like they organized from smallest to largest, which is nice of them. It doesn't look like 381, 384, right? Up here we got 408, 411, 413. No, there's really no outliers here. So mean would be the best way to show my center of data that would summarize that data. Okay, and then the last 9 calls to a customer support line had the following lengths in minutes, 22, 23, and so on. Which measure should be used to summarize the data? So we're looking for something that would show me the center and a mean or median. Now the only problem is, now this stuff looks good, 22. What I mean by good is it looks like, I don't have any great outliers, 28, 30, but wait a minute. 65 is a big time outlier. And so I better not use mean because it's not resistant to outliers, but median is. So median would be the best one to choose. All right, this whole idea of outliers, that used to kind of bug me before, because it just felt kind of wishy-washy, like how do you know if something's too big? Now that I think is pretty obviously quite a bit bigger than everything else, but we will have a standard rule that helps us definitively chuck out outliers. It's not just like, okay, I think that's too big or I think that's too small. There's actually a little equation we can use. And that is it for today. Thank you very much. I hope you have a great day, and I hope this 3.1 from the adaptive side of ALEKS helps you with your work. Take care. Have a good one.